Okay, so we're looking at example 2 here, and you have quite a bit of information for it already. So we have a KSP, and it is 1.1 times 10 to the minus 18. They do tell us about the temperature. It's at 25 degrees Celsius. For the short term, the temperature doesn't matter. There are questions later down the line where the temperature plays a factor, but for now, we know the temperature is relatively staying the same, which means we can ignore it. So the KSP for mercury 1 chloride. What's the formula for mercury 1 chloride? Write it down.
HGC. It's on there. Mercury 1.
Yeah. So the mercury 1 tells us the charge of the mercury. So we've got this Hg with a 1 plus and a Cl with a 1 minus, and take over that C, H2Cl.
Well,
so when we dissolve this in water, we end up with.
Wait, why does it have Hg2Cl2 on it?
Oh. It's on our list of ions. That's a crazy one. All right, so let's use Hg2Cl2. If you look at your formula sheet, and not the formula sheet, but
so it should be mercury 2.
Is that still mercury?
the ion
Oh
sheet.
my God.
Yeah, it's something weird. So we'll just follow the page. Personally, I would reduce this, but that's not the way they got it listed here.
Oh, yeah.
What is it that scientists do this?
Mercury 1 has a +2 charge.
Yeah,
What?
Hg2 2 plus.
How does that work?
Mercury is one of those exceptions. Now that we've got it on the board, let's just go with it.
Why would they call it mercury 1? Just to be like pretentious.
I guess. And so let's change this to reflect it.
They call
The
the +1 charge mercury 2.
Hg2 2 plus. All right.
No, they're both plus.
So now that we're following the paper, and 2 chlorides. So here's the reaction. So 9 times out of 10, when they tell you the KSP for this compound, they're not going to give you the reaction. And I think it was earlier on this page, it says that KSP implies a dissociation reaction, which would be, this is the dissociation reaction. So you're usually not going to get, this is the salt, this is dissolving. Question says, calculate the solubility. Solubility. What does that sound like? Molar solubility? They're interchangeable terms. So we are looking for S, the molar solubility. And then after that, once you get that far, you might as well find the concentrations. But let's find S. So let's go ahead and make an ice chart here. Kind of a tight chart. All right. So at the beginning, we have a certain amount, and we're about to put it in the water. There is no mercury 1 in the water. There's no chloride in the water. That's a good thing, right?
Or chloride.
So we know that when we start putting this mercury 1 chloride in the water, that some of it will dissolve, which means that we are going to have more mercury in the water. It's increasing, it's positive. It's going to increase by some amount. Coefficient is 1. It's going to increase by 1 times S. S, the solubility, or the molar solubility. Every time we dissolve that, we're going to get plus 2S for the chloride. And so my equilibrium concentrations are S for the mercury and 2S for the chloride. All right, so what do I know for this column right here? Do I know the initial? Do I know the equilibrium? Do I know anything? Anything important? Anything helpful?
You don't do solids, right?
You don't do solids. Stay out. S means stay out. So we can completely ignore that column. So we can find S. In order to find S, we have to plug it into some sort of an equation, KSP expression. So we need to write the equilibrium expression for this KSP. And it's going to be in terms of concentration and brackets. So KSP equals, the products go on top, concentration of mercury times the concentration of chloride squared. Remember, solid S, stay out. It doesn't go in this equilibrium expression. And so this is the expression. We plug in our numbers. Hg is S. Chloride is 2S. And we have to square it. So we end up with 4S to the third power. We also know what KSP is. So 4S to the third power is 1.1 times 10 to the negative 18th. And we solve for S. Does everybody agree with Charles? He did say it pretty quietly. Yeah, I'll write it for you. 6.5 times 10 to the minus 7. Everybody agree?
I do.
Disagreeing with yourself. So a lot of times in a solubility question, they'll give you all the information that we see here, but they're not usually saying solve for the molar solubility. Usually what they're going to ask you when they give you this, they're going to say, what is the concentration of this? And what is the concentration of this at equilibrium? And so the equilibrium concentration of mercury 1 is S, which we already found at 6.5 times 10 to the minus 7. What are my units here? You're going to have units here, molar. Concentration of Cl minus at equilibrium is 2S, and so we have 2 times this number. .3 times 10 to the minus 6 molar. So we found the equilibrium concentrations, and we didn't even know how much mercury 1 chloride there was to start with, because we didn't need it. We can figure out all this stuff without even knowing how much we had in the beginning.
Can you get some mercury out and toss it around?
Toss it around.
And have it all over our hands, like in our eyes.
Wow, sounds wonderful. In your eyes.
We boil some mercury.
What's the bad idea?
Charlie, do you have a death wish? Just out of curiosity.
These all seem like great ideas.
Charlie's chock full of them.
Officially, I don't have any mercury. Let the record show that we do not have mercury here. All right, example 3. Rank the following salts in order of increasing solubility. We have cobalt 3 hydroxide. KSP is 2.5 times 10 to the negative 43. Lead 2 phosphate, KSP 1 times 10 to the negative 54. 10-2 sulfide, KSP 1 times 10 to the negative 26. It says rank the following salts in order of increasing solubility. So there's something we need to write down. I'm going to go word for word, so this might take a minute. Okay, write that down, then we'll talk, and this will be the last one we do before we're done.
We need to write that too.
You already have this stuff written down. Okay, so in general, the KEQ or the KSP will tell us the extent of how far it's going to go. So from a general sense, these KSPs will tell us which one is more soluble than the others, but it's more complicated than that because for solubility, we're actually talking about S. And S has to do with other factors like how many ions are present in each one. And so the KSP and the S are related, but there's an equilibrium expression involved. And so the first thing that you're going to want to know is what's the formula of these different compounds. So cobalt 3 hydroxide, cobalt 3 plus, so that means 3 hydroxides. So there's the first one. And when it dissolves, you end up with this and 3 of these. Lead 2 phosphate. So you've got this compound as the solid. Here, just breaking up into its 2 ions. 10-2 sulfide. This one's actually kind of easy.
What was the letter short for? First PB.
What's that?
What is it called? PB.
Plumbus.
Plumbus.
Latin. Plumbus. Lead is what they used in their plumbing, and it was untreated, so they all got lead poisoning. All right, so the reason we wrote these out is because we need to write the equilibrium expressions. But we can kind of do the shortcut method here since we already know what's going on. So for the cobalt 3 hydroxide, instead of writing out the whole expression, you could just say there's one of these, so that's S, and there's 3 of these, so it ends up being 3S cubed. Am I going to lose anybody going the shortcut method? And we know what the KSP is, so we put it in here. And then we can solve for S. So I've got it here, 9.8 times 10 to the negative 12th molar. And we do the same thing for these other ones. PB3, PO2. So for the lead, we have, it's going to be 3s to the 3rd power. We've got phosphate, which is 2s to the 2nd power. And the KSP, which is 1 times 10 to the negative 54. When we solve for S, it's 6.2 times 10 to the minus 12th molar. And the last one is just going to be S times S, 1 times 10 to the negative 26th. Solve for S, it is 1 times 10 to the minus 13th molar. Which one had the biggest KSP? Which one was supposed to be the most soluble based on its KSP?
Oh wait, no, that'd be 10 sulfide.
10 sulfide. So lead phosphate should have been the least soluble, But when you break it down by these numbers and look at the solubility, it's actually the most soluble, right? Or that's in the middle. So this is just to illustrate that you can't just base your ideas off of the KSP. S is a more reliable indicator of the solubility. So kind of the bottom line there.
What does S have to mean?
What's that?
What does S mean?
Solubility.
Right. What was that?